overall memory that I have from Antarctica is euphoria. You are driving on the skidoo and everything you see around you, it's a white desert. The noise level is very low and the illumination is very strong. Our lab study light harvesting by aquatic microbe, and it simply means that we study the molecular mechanisms that allows microbes to use sunlight as their source of energy. As far as we know, there are only two molecular systems that enable this process. The first one is photosynthesis. The second mechanism is known as the rhodopsin protein. It's a much simpler molecular system that contains only two components. A protein that is attached to a very special molecule named retinal, and this retinal is responsible for absorbing light energy and activating the protein. And this is the most simplest way that microbes can use to harvest sunlight energy. During the winter, there is a formation of a huge ice sheet around the entire Antarctic continent, and the idea was that rhodopsin protein allows microbes to survive in this very special environment. For several months, bacteria are locked inside very small air pockets, so the conditions that they are exposed to are very constant. So going to Antarctica, to this sea ice environment, is very convenient for us to study. The first moment you step out of the plane, you are completely shocked. You are struggling to understand what you are allowed to do and what is dangerous. Everything is different, everything is new, everything is much harder. You need to drill the core, or you need to extract ice sample and then melt it, and on top of it, you need to take into your consideration the weather, which is very unpredictable. When the wind picks up, there's nothing you can do. You have to find a shelter because it's like small knives that fly around, and of course you cannot run experiments, you cannot move around, and you have to stay in camp and somehow kill your time. Traditionally, we treat rhodopsin as a two-component system, right? Protein plus retinal. But recently we published a paper in Nature journal that reports on a very large breakthrough that many rhodopsins can bind a third component, an additional antenna that capture more light energy and enhance the activity of the complex. What is so special about it is that it absorbs light within a specific wavelength range. And to the bottom part of the sea ice column, most of the light that is available there is exactly the wavelength range that is preferentially absorbed by the third component. So our hypothesis is that the bacteria that live on the bottom part of the sea ice column will preferentially use three-component rhodopsins versus the two-component rhodopsins that were known before. I'm the only representative of the lab that's joined to the New Zealandic team. And it is challenging, but I must say the New Zealandic team received me beautifully. And all in all, it was a beautiful social experience. Sunlight is one of the most predictable and reliable sources of energy that you can find in aquatic environment. So studying the ability of this specialized microbe to use this source is vital for our understanding of the main flux of energy into the microbial system and for the entire food chain.